In the study of mathematics, we often get lost trying to categorize or find out and memorize all those formulas and properties and ideas that we've learned through our entire mathematical career. And today, I'm going to be introducing another very important idea in mathematics. But before we do that, I want to step back and talk about something very exciting and abstract, which has to do with kind of the way we interpret and understand everything that we've learned in mathematics thus far. And what I'm going to refer to is something called mathematical entities or mathematical objects. And what do I mean by that? Well, what I mean is that a mathematical entity is like a thing in math that is also equipped with an operation. And we'll give some examples, of course, but this is a little bit of a foray into what's called group theory in abstract algebra, which I really encourage you to check out on Wikipedia or somewhere else. It's a very interesting topic. So let's just get into an example. And you've definitely seen these before, many of them at least. So we can split these mathematical entities into different tiers of perhaps when we've seen them or their importance or how often we see them come up. So the first tier, as I like to call it, will be what we call numbers. And what do I mean by that? Well, numbers are a thing, and they're equipped with several different operations. You can add two numbers, you can subtract two numbers, you can multiply two numbers, right? And you can divide two numbers, right? You can also exponentiate them. You can do a to the power of b, or you can take the nth root of a number, right? Like the square root of 2. It's an irrational, but it's a number. So these are several different operations that numbers work with. And so that's an example of a mathematical entity. It's something we can call a group, if you will, not in the formal ways defined in group theory, but it's just a thing that can also be performed with an operation. So the second tier, we can say, is sets. So the second tier of mathematical entities we call sets. Now you've seen sets before. For example, numbers fall into sets, and now you can see the higher tiers really showing up. So for example, sets can include the set of natural numbers, right? Or the set of integers, the set of positive integers or negative integers, greater than or equal to 0, the set of real numbers, or just the set of all numbers that follow a certain pattern, a sequence of sorts. And there are several different operations that we do with sets. You can take the union of two sets, which just means you take all the elements in A or B. So again, often you draw a Venn diagram of the two sets, and A union B would just be the entire section here shaded in. You can also take the intersection of two sets. So for example, you have A intersect B, which just involves taking the elements of both sets that are shared, so the center section over here. You can take the complement of a set, so it's written like A complement. So these are operations. All the items that are not in A, which would include everything in B minus that intersection, right? And you can express these operations in terms of others. You could also do set subtraction, A minus B, where you subtract elements of sets. And not in the way you would subtract numbers, but in the way you subtract elements of sets. So there's a different level to the kind of complexity of this situation. So that's the second tier, sets. Now, the third tier you've definitely seen before, and those are called functions. Now, why might functions be the third tier? Why might they be a tier above sets? Well, a function, remember, maps one set, a domain, so I'm going to call it D, and it maps that to a range, R. And these are two sets. Domains are the sets of all numbers that a function is defined at, and the range is the set of all the outputs of the function. And so that's why functions are just one tier above sets. Now you have operations with functions. You can compose two functions, so you could have f of g of x, right, written either like this in what I call fog notation, fog x, or you can write that as f composing with g of x. You can also invert a function. Functions are sometimes invertible, so they can have an inverse. So f inverse exists, right? So then f inverse of f of x should equal x and vice versa. So that's another operation. You can invert a set, inversion. You can also add functions, subtract functions, multiply them, divide them. And they include operations with numbers. So functions can also take on numbers. So for example, if a number a is equal to a number b, then it's logical to assume that the sign of a is equal to the sign of b. And that's why functions are operations with numbers, all right? That's a very important idea for functions. Now, what's a separate tier. This might not be a tier above functions, but I'll show you how you can interpret it as such. But we have vectors. Now you may have seen vectors before in linear algebra, but if you haven't, don't worry. A vector is essentially an object that has a magnitude or a size and a direction. So for example, if you're walking across the street, there's a certain vector along which you walk, right? So there's a path. It's basically a path. Now in more abstract scenarios, you'll see that vectors are not seen as coordinate numbers. So again, vectors can be expressed as coordinates. So you can say 2, 1 is a vector, which essentially means you have 1, 2 in the x and 1 in the y coordinate, and the vector is an arrow from the origin ending with the head at that point. But in abstract algebra, you'll see that vectors are simply just objects that have operations equipped with them. And what are these objects? Well, you can add two vectors, right? Adding this vector to a vector like this gives you the net displacement, which is this vector. So it's not addition of numbers in the traditional sense, right? You can also subtract vectors, which just means adding them by a negative factor. So that's the same thing as scalar multiplication. If you have a vector v that looks like this, you can multiply it by a constant c, which ends up just multiplying the outputs or the inputs of that vector. So ca if a is an input, and cb if that's an input, like this, right? So you can do scalar multiplication. You can add vectors together. You can do what's called the dot product of two vectors, which is an incredibly important operation, which is sort of analogous to multiplying two vectors, but not in the traditional sense. It has to do with adding the sums of the pairwise coordinates of these vectors. You can take an operation called the cross product as well, where you're essentially generating a new vector, because this output here from the dot product is a scalar, while the output of a cross product is a vector in 3 dimensions, which essentially, simply put, is if you take a vector A and a vector B, then the cross product will give you a new vector that's perpendicular to both others in 3 dimensions. And its direction depends on the order with which you multiply these two. These are non-commutative. So A cross B is not equal to B cross A. So these are just some examples of operations you can perform with vectors. Now, how can you look at a function as a vector? Well, functions can be seen as vectors if you take a look at, for example, a function like f of t, and you make that have two outputs, where the x-coordinate is always t, and the y-coordinate is always, let's just say, sine of t. Now, what does that mean? That means that for every x-coordinate of t, you just get the x-coordinate. This is a set of all points such that t and sine of t is satisfied, which is basically what a function is. So this vector graph here will just show an arrow from the origin tracing out the shape of sine of x at every point t, or sine of t in this case, in the t-axis. So functions can be seen as vectors. Now, one step above vectors are matrices, and these are incredibly important, okay? Matrices you'll see if you take multivariable calculus, and you'll see matrices in linear algebra. These are essentially functions that input vectors and output vectors. So as you can see, we've had functions a tier above numbers, and now we have vectors above functions and matrices that are functions that take in vectors. We're going crazy now. And there are so many operations you could do with matrices. For example, a matrix, which is in the simplest sense a kind of array of numbers, of values in a table up like this in a little square bracket or a different rectangular shaped bracket. And matrices can be added together. So if you have a matrix A, you can add it to a matrix B, which just means that you add the coordinate, or not the coordinates, but the entries in each of the little areas here that correspond to each other. You can also multiply matrices by a scalar. Multiplying by a constant c, or let's just say use k here because we have c here already, is the same thing as multiplying each of the entries by that constant k. You can also invert matrices. Matrices have an inverse, which in certain cases, just like functions have an inverse. You can compose matrices, which involves multiplying them, and you can in fact multiply matrices, and their order will also be non-commutative, not always commutative. All right. There's an operation where it's called the transpose of a matrix, where you're essentially switching the rows and columns. So here, the transpose of this sort of matrix would just be A, C, and then B and D, because you're just swapping these rows and columns together. Okay? So the transpose is another operation you can do. And even deeper than that, you can also take a matrix and exponentiate it. You can raise e to the power of a matrix. And this is some really serious stuff here. And this has to do more with a lot more complex things. So don't worry about that if you're feeling intimidated. But there's so many operations you can do with matrices, which is why they're so high up in this tier of mathematical entities. But the sixth tier that I'll show you right now is incredibly important, and it kind of factors in a lot of the previous lower tiers. And this is where I'm going to introduce you to operators. Okay? Operators. What are operators? Well, operators are things, essentially, that act on both sides of an equation. So, for example, functions, f of x, are operators with numbers. So again, like the previous example, if a is equal to b, then logically, if we apply sine as an operator, meaning we apply sine as a function to both sides of the equation, then we keep the original equation as true. Sine of a should equal sine of b if a is equal to b. Or, if a is equal to b, then e to the power of a should be equal to e to the power of b. And this is called the exponentiation operator, exp. So again, functions can now be seen as vectors, they can be seen as operators, which is going to be incredibly important in calculus. So for example, sine is an operator, which you can write in capital sine, cosine is an operator, tan is an operator, all those functions are operators. You can take the natural log as an operator, which is just the log operator, or exponentiation, e to the power of something. Exp is an operator that acts on both sides of the equation. But what else can be seen as an operator? Well, if f of x is equal to g of x, then isn't it logical that the derivative with respect to that x of f of x should be equal to the derivative with respect to x of g of x? In that sense, the derivative is also an operator. So we can write that as a kind of curly d like this that acts on both sides of the equation, or what's called a differential equation. So that's the curly d. So derivatives are operators. Now, what else is an operator? Integrals, which are sort of seen as the inverse of a derivative, are going to be also operators. If the function f of x is equal to the function g of x, right? If they're the exact same function, then logically the area under the curve of one function is equal to the area under the curve of the other function. So integrals are also operators, which can act on both sides of an equation. In this case, we have indefinite integrals, all right? What else is an operator, though? You might have seen it before, limits. Limits are in fact operators. And where have we seen limits used as operators? Well, if you've done a little studying in calculus and you've seen the squeeze theorem that says that if two functions or three functions are kind of sandwiched in a way such that one function is always greater than or equal to the other function is greater than or equal to the lower function, then, and they all have, and the upper and lower functions, have the same limit at a certain point, then the middle function is squeezed between those two functions and has that same answer of the limit at that point. So in a way, if you have, let's just say, f over here, you have g on the bottom, and you have h on the top, where let's just say that they have this weird behavior where they squeeze the function in the middle at some point like this. And we're just going to extend this function like here, like this. So this is the point at which everything's squeezed together. Then you have f is greater than or equal to h, which is greater than or equal to g. And at some point, at this point here, what we can call c, the limit as x approaches c will be equal. And we can see that with the squeezing here. So in a way, we can apply the limit as x goes to c to all sides of the equation to verify this. And this can also go to infinity and everything else. So in fact, the limit is an operator when they approach the same value. Now, the other thing you can do with operators, because I haven't actually said what you can really do with operators in terms of operations with operators, right? They are a mathematical entity, so they need operations equipped with them. Well, you can undo operators. If sine is an operator, then arcsine can also be an operator, the inverse sine, that'll undo it. Or like here, we have log and exp. These are inverses of each other. Or derivatives and integrals, those are inverses of each other. So whenever you do one operator or make one operator on two functions, you can revert that, and you can use the inverse of that operator in many cases. So operations and operators are invertible, and moreover, operators can be added, operators can be subtracted, which is a bit more kind of in discrete senses, but they can also be composed, right? You can take the derivative of a function and then apply the sine operator, and then you can apply a limit, and that's essentially the same thing as composing all of those things together. So again, why are operators so important? We're going to be using operators a lot in calculus to help solve difficult problems and to derive important results. So for example, logarithmic differentiation, we will see in a future video, will involve operators. Exponential differentiation will involve the exp operator. Trig operators are going to be used to solve derivatives of trig functions. So there's a lot of exciting things to do with operators. So stay tuned, and remember that math is beautiful. So step back for once and just look back and reflect at everything that you've done. Till next time.